Here we will run an experiment and prove that light refracts and even bends in the air. We will show how this affects the famous stick and shadow experiment. We will show that the method by Eratosthenes to prove a round Earth is completely unreliable. We will show how refraction can cause the sun and moon to curve towards you. We will explain why refraction is one of the most important topics in flat Earth and how it works greatly in favor of it. Other topics covered will be the stratosphere, density gradients, Snell's Law, Fata Morgana and Mirages, Nikola Tesla, the Sun Calc website, sunsets, the azimuth equidistant map, the false math of relativity, the diameter of the sun, the moon's face, light speed fallacy, and several other topics. If you want to see specific topics, here is a table of contents. However, we recommend that you watch the entire video, especially the parts on refraction. In our last video, we proved that air density can cause the sun to get cut off from the bottom because air isn't transparent. However, now people have asked about the sun's position in the sky and its elevation angle and if it could truly set based on estimations of its size. I've decided to make one final video on the subject to cover other important topics, a few which have not been discussed yet in the Flat Earth movement. In the experiment, we made sure to make accurate measurements to determine the altitude of a laser pointer using the stick and shadow method. We simulate refraction in the atmosphere using a pail of water. Then we triangulate the difference in altitude. First, you can see the setup of this experiment so you can try it at home. You would need a laser pointer, a pail of water, a thin stick, and a tape measurer. We made measurements and marked them. We ran the experiment several times and with different lights. The stick and shadow experiment method of measuring the sun's distance is one of the oldest round Earth experiments. It was widely ignored for thousands of years by all of the major cultures and religions until the theories became popular again in Europe. The technique involves measuring the height of a shadow compared to the object that casts it. Then you have a right-angled triangle. If you measure the distance of that city to a second city or a city that is 90 degrees below the sun, you can get a very good guess of the height of the sun. Eratosthenes guessed that the Earth might be round because he was unable to get an accurate lock on the sun's altitude from this experiment. It's worth pointing out that the stick and shadow is much worse at predicting the sun's altitude in a round Earth, and it is not even used to do so. The experiment is a complete fallacy, mainly because the atmosphere is layered. These layers create a density gradient. Each layer will refract the light in a different direction because the refractive index of the primary elements it contains will be different. From our example, we prove how when moving from air to water, the shadow will increase, resulting in a lower than expected elevation. The reverse is true when moving from water to air, or more specifically, from a high refractive environment to a low one. Here, you can see us move the water in and out of the path of the laser. There are a few things that happen. First, the shadow length increases a couple of inches. Also, we can tell that the position of the light on the ground has changed. Additionally, the diameter of the light has increased. This works against around Earth, especially when they say they don't see an increase in the sun's diameter at sunset, mainly because the sun would pass through water and other refractive mediums and absolutely increase its appearance if their claim had any truth in it. Furthermore, you can even see the angle change within the water, which is quite beautiful. If we film from under the basin, we can see the sun change positions. To prove that the plastic container does not greatly exaggerate the shadow or light, we remove it from the light. Although it does cause a slight difference, it's not as significant as the water. We take the water out of the container and pour it back in. In this segment, you can watch as the shadow grows in the light. You can also watch the light change positions on the ground. And here, for comparative purposes, we shine a regular light on the stick. Here we show how the shape of the container, such as in the case of a cloud, can do the reverse and shrink the shadow, causing the appearance of a higher sun. We show side by side a ball of crystal and the round water container. At the conclusion of this experiment, we triangulated the values of the measurements to show the difference in altitude. The results are shown here. In a moment, we will teach you how to triangulate these. Many flat earthers say the sun is 3,000 miles up. It is unclear what experiment is used to know the true height of the sun. Our guess is no such experiment will exist anytime soon. In any case, this would mean a 25-degree elevation angle at sunset. Obviously, even with air density blocking the sun, that is hard to justify. It turns out that the sun and moon tend to set on the horizon at roughly 10,000 kilometers away from the observer. If the stick and shadow experiment changed due to atmosphere, the question remains, in which direction does it change? And how does this affect both models? First of all, for every question we answer, there will always be two new questions. We are all in the search for truth. with the exception of the enemies of truth, of course. The question you need to ask yourself is, what model has greater margin of error, a flat Earth or a round one? In the game of pool, the longer the shot, the more difficult it is to make. If you are going to claim the sun is 93 million miles away, even the slightest change in angle of elevation will debunk your model. Let me introduce you to the absolute beauty of refraction. In this video, you can see how light bends in water. In our experiment, the angle was straight, but what's happening here? Why is light bending? Well, the best part is you can repeat this experiment at home. You just need a pail of water, some sugar, and a laser pointer. In our last video, we discussed buoyancy. Well, the sugar dissolves in the water and then goes to the bottom of the pail. To make the experiment even more fun, try adding different dyes or even try adding oil. You can see in each medium the light's angle will do something completely different. This is what is called a density gradient. Our atmosphere is a giant density gradient. It is filled with many different chemicals. The troposphere contains a lot of water. Humidity can be 30 to 70%. The lower atmosphere is mostly nitrogen and oxygen. It also includes argon, helium, hydrogen, methane, and many other chemicals. There is other levels of the atmosphere, unfortunately off limits to citizens. The highest unmanned balloon a citizen has launched into the sky was 53 kilometers. Because of buoyancy, helium and hydrogen rise. Therefore, there is a tremendous amount of those elements in the stratosphere. There is the ozone layer filled with O3, oxygen, and there is the magnetosphere. The magnetosphere can ionize the air, and obviously a magnet can have a profound effect on light. This effect is called the Faraday effect. It's where the polarization of light is rotated while it travels through transparent materials. There are many lab experiments to show electromagnetic effects on light. Also, this is a field that requires a lot more study. Some scientists say that magnets don't affect light, but consider that light is moving at extreme speeds. So a single magnet may not be too noticeable. However, a giant magnetic field such as the Earth's field can certainly affect light. As you can see, buoyancy absolutely must separate the elements of greater densities. This means that NASA is clearly not telling us the truth about the elements contained in the stratosphere, and they are probably not telling the truth about the air pressure there either. When hydrogen and helium rise, they obviously do not disappear. No, they settle at the top and they stay there. It is almost unbelievable to say that nitrogen is the most common element in the sky when there is so much helium and hydrogen rising. Not to mention other combinations thereof. Take a look at our buoyancy diagram. This is what we call a density gradient. The cutoff lines are actually pretty clear. Let's take a look at a density gradient in a laboratory. Here we can see that the light is bent downwards and then it is bent upwards. In fact, they even split the beam of light and recombine it later. Pretty amazing, right? Still not convinced? Take a look at this clip from the North Pole sun mirage. They see the sun during a time of the year where it should have been impossible. It may be due to the magnetic pole or some other refractive phenomenon. There have been many experiments to show how light can bend up or down in our atmosphere. Over the water, it would be more probable that light bends downwards very slightly near the ocean line as light descends. This is because, as you get closer to the water, the amount of water particles increase. This increase in density causes light to go from a refractive medium to an even more refractive medium. This is called Snell's Law. This could add to the list of possible causes for cities to get cut off at the bottom over the water line. What's cool about Snell's Law is when you send light back angled up from the water, the light can actually bend upwards. This has been seen in different flat Earth laser tests. The experimenter has to be extremely careful to keep the laser as straight as possible, and over several miles that becomes almost impossible. Imagine shooting a pool ball into a hole 10 miles away. Snell's law is basically an equation that is used for calculating the change in angle of light as it passes from one medium to another, so we can mathematically compute and guess how much light might bend in each medium. Let's take a look at a refraction simulator online. First, you can calculate light going from air into water, like in the case of a city. Remember, the city is on land, so the water density is lower there. As you can see, the lower the altitude of light projection, the more the light falls when it hits the water. As you can see, the sharper the angle of the light, the more the light falls when it hits the water. This works in favor of a flat Earth in any case, because a city skyline would have more trouble curving over the horizon when moving from air to water because it refracts light downward slightly. However, if you are in the ocean and you shine light upwards, the reverse happens. Let's take a look at what happens when we go from water to air. Amazing, right? The broader the angle of the light source, the less it refracts. Although in our atmosphere these changes are subtle, they are significant over many miles. Let's take a look at this site here. They sort some elements by their refractive index. Notice that there are still tons of materials not on this list, and they do state that the numbers need to be verified, but this is a great reference. So we can see that hydrogen is 4 times more refractive than helium, and lucky for us, hydrogen is more buoyant. So for the 300 or more miles of atmosphere, depending on how high you guess the sun to be, light will travel significant distances bent upwards towards the observer. Extreme heat or cold from the sun can certainly forge elements, such as helium hydride or even stranger elements. It's fair to say, unless parts of space reach negative 300 degrees, we will probably not see liquid hydrogen. However, on the internet, people seem to say in some cases atmosphere is extremely cold. It creates an inversion layer, supposedly. Maybe it just depends on where the sun is. It has been estimated that there is helium hydride in the stratosphere, however. Now, if we consider that hydrogen is above helium, this element will form a nice little lens compounding the amount of refraction that the light experiences. Even a thin layer would be significant. Imagine the light passing through hundreds of tiny little lenses. In order for helium hydride to exist, it must be in an excited state, and I think the tremendous heat of the stratosphere would be a good catalyst for this. I would like to see some experiments done with refractivity of exotic materials like these. I expect it to be significant. You see, an element on its own is not even close to the refractive index of a combined element, and the direction of refractivity may indeed change depending on the combination. For example, water is significantly more refractive than hydrogen or oxygen on their own. Why the dramatic change? Because the elements form a little lens. Let's take a look at the periodic table sorted by density. Using this, we can know how some of the elements will be ordered in the atmosphere and what direction light will bend for each layer. But don't let that dominate your calculations, because what matters is the amount of miles light will travel at the angle before crossing into the next medium. Also, it matters greatly the different materials in the atmosphere. Do not limit your bias to elements only. Refraction increases dramatically when you combine elements. For example, how does ozone affect and refract light, and how thick is the layer? Don't count on government space agencies for honest statistics here. For example, when light goes from helium to lithium, lithium is only 0.23 refractivity, and helium is more than 4 times more refractive. So again, light refracts upwards, and quite significantly. Lithium passes to argon, and light will refract downwards, and it will go down again from argon to nitrogen, and then again slightly from nitrogen to oxygen. However, a big change will happen when light passes through the water in the upper atmosphere to air, which will refract light upwards again. It's hard to say how much argon or lithium is in the atmosphere, however. Ionized particles need to be considered too, and particles such as dihydrogen, dioxygen, and so forth. It's no surprise that people see sundogs and other anomalies in the sky. If you consider that dihydrogen might exist in the hydrogen layer of the atmosphere, then when moving into helium, the refraction angle will be very significant. Light will bend for potentially hundreds of miles up towards the observer. One quick note before we proceed. Explaining our world is not easy. We realize that there will be some debate over how much light is refracted, at what point light refracts up or down, whether or not there is a dome, and so forth. We are not trying to add to the list of theories. We are simply pointing out a scientific fact that absolutely 100% must be discussed. I'm going to assume that because of how many factors there are involved, that being able to calculate this mathematically is actually impossible. However, lucky for us, we have evidence that works in favor of flat Earth. It's called advanced sunrise and delayed sunset. This is where the sun sets later than it should. Sometimes the sun rises earlier than it should. This is evidence that sun's light bends upwards towards you. In fact, even according to Wikipedia, which is usually very anti-conspiracy, the sun has been seen to set and then rise again, only to set and rise within the same hour. This can be found under the entry for atmospheric refraction. Although I don't really like using Wikipedia, since news articles have been published showing the majority of Wikipedia edits in some categories come from CIA data centers. But let's use it anyways to get some ideas. First of all, their image for the sun is totally bizarre. Why do they have the sun's rays pointing upwards and then bending downwards? Don't the majority of the sun's rays come in straight? In fact, if the atmosphere bends light towards us, why does it ever get dark? Isn't the sun billions of miles in diameter? Anyways, the actual diagram should look something more like this. Here the light comes in straight and bends up, just like we calculated. First off, it says astronomers will never shoot a star 20 degrees below the horizon because of refraction. Then it says that refraction is caused by the temperature gradient, the temperature, pressure, and humidity. This is extremely interesting. Did they forget the refractive index? We just got finished looking at refractive indices, and they ignore it. But they add some useful information, temperature. This is a huge factor in refraction. You see that the atmosphere gets extremely cold in some places and extremely hot in others. You will see how much this matters in a moment. Here they say something else. They say, when the bottom of the sun touches the horizon, its true altitude is negative. Did you see that? That means it shouldn't even be there. And since they are assuming a curved Earth, imagine if they assumed a flat Earth. That would really change all of their calculations. It then talks about an example once of how the sun set only to rise again an hour later. That's right, an hour later, and then it set an hour after that, and then it rose, and then set again within the next 20 minutes. This is a classic example of advanced sunrise and sunset. Then they give some formulas, although these formulas might be kind of useless because they would have to know the exact elements contained in the atmosphere and the changes in temperature, especially in the thermosphere. And then a calculation so complex would never be reduced to such a trivial equation. However, this formula is interesting. Here it says the amount of refraction increases 1% for every 3 degrees decrease in temperature and increases 1% for every 3 degrees increase in temperature. How these were arrived at is not really clear. It looks like they base this off of the previous equations and more assumptions. The numbers seem way too linear, but if this is true, then the extreme cold or heat would dramatically change refraction. Is there an experiment we can do at home to prove this equation? Probably not. And I'm sure it wouldn't really give us any help on the extreme heat of the sun and how it affects things. After all, on a hot day over the road, light starts bending all over the place. We can probably just relate this to pressure and density. Cold air is more compact with more molecules, and hot air disperses with less density. So that affects the density gradient. This is why hot air balloons rise. They say you can see certain dispersed wavelengths with a refraction corrector, which is a rotating prism. But I doubt this would work over long distances because that light could easily be blocked and reflected. Also, the refraction of light makes the calculation of stellar parallax completely impossible, especially on the ground. In fact, refraction pretty much debunks the idea that stars are traveling up to 1 billion light years to reach us. The probability that light would be refracted, curved, and generally moved all over the place, it may as well be 100%, since they're saying that there are stars that are quintillions and septillions of miles away. Even a change in a trillionth of 1 degree would cause the light to miss the Earth completely. At the very least, you would see stars disappear for a little while to reappear again. Have you ever watched a light moving in water? Notice how it bounces all over the place? It's convenient for NASA that they'll tell you that space is just infinite miles of vacuum, even though they've really never been out there. This is probably another reason they tell you the galaxy and solar system are flat, to avoid the amount of protests they would get otherwise. Also, if astronomers avoid filming stars 20 degrees above the horizon because of refraction, that alone is enough to prove to you that their calculations of parallax are not scientific or reliable. If you triangulate a 10,000 kilometer sunset at 300 miles high to the ends of the stratosphere, we get a 2 to 3 degree angle of sunset. This certainly makes the sun easier to block with air. In fact, anything within 10 degrees is worth discussing. Another reason why this subject is so important is because it can potentially explain why the moon only shows one face. Flat earthers tend to ignore this problem. The moon, no matter where you stand, shows the same side. What type of magic holography is this? Well, if you consider that the atmosphere is potentially bending light towards the observer, then it makes sense that a flat light would change its angle towards us in the atmosphere. Let's take a look at some different types of holography while we are on the subject. Here you can see a coin appear on top of a cylindrical base. No matter what perspective you view the mirror, it looks like the coin is sitting on top of the base. Try to grab it, it's not there. The trick is in the mirrors on the inside, a brilliant little design, like a cylindrical pepper's ghost. Of course, there are almost endless ways to design a system like this. Now let's take a look at lumographic lenses. These things are completely awesome. Depending on the angle that you view the lens, you can see a different image. This type of lens is an art form. And here is cast-AR augmented reality glasses. They use 2 projectors and reflect them off of a retroreflective surface back to your eyes. Everyone sees a unique image. Anyone can make a pyramid hologram at home. Here I filmed a holographic moon myself using a simple pyramid made from my transparent sheets. For those people who theorize that there is a dome or firmament above us, whether it is made of ice or any other material, that could definitely reflect light back to the observer at various angles. In addition to reflected light, there is projected light. Light from a projector expands as it moves away from you. However, this also depends on the shape of the lens. A flat light source like a television screen would cause almost no increase in size as you move away from it. Perhaps this is why the moon and sun have a slightly round appearance. It would also be another possibility to explain why the sun does not shrink as much as people anticipate. Also, the further you are from the sun or moon, the sharper the angle is to them and the greater the refraction. Also, the more miles the light must travel through the thermosphere to reach you, and the more profound a small change in angle will be. Have you ever seen a moon set? Have you noticed that it almost always seems to move faster in the sky the last few moments as it descends? The sun seems to do the same thing. Right before sunset, it quickly drops a few degrees. Why? Finally, on this subject, we can see hundreds of examples of sundogs, double suns, double moons, and other things like this in the sky. It's hard to make sense of these sightings and decide which ones are valid. However, multiple suns is a pretty common occurrence. Also interesting is the alleged sighting of Rahu, which is a semi-translucent disk said to be the cause of eclipses. Something similar to this could cause the moon's phases. Or, considering that the sun and moon are constantly refracted, this introduces a wide new range of possibilities for the moon's phases. So let's check out a website called suncalc.org. Many flat earthers come to this site to attempt to measure the sun's height in the sky by triangulating elevation angles. First of all, how does SunCalc know the elevation angles? It doesn't. They guess them based on what they believe the curvature of the Earth to be. Although the angles have just been completely disproven, let's make some observations. If we use this site, we can find out that the sunset almost always happens at 10,000 kilometers away from the sun, or 6,200 miles. This means roughly the elevation angles the site gives you will go down 9 degrees for every 1,000 kilometers from 90 degrees dead center. You can test this yourself. There will be some variations. Let me show you how to calculate the sun's height in the sky. It's easy when you know how. I chose a city that was on the equator with a 90-degree elevation angle to the sun and at sea level to make this very easy. Then I chose multiple cities at random. I will link my choices and results in the description. Now we measure the distance of our cities by using the longitude and latitude. I'm going to use Google Maps. However, before I proceed, there's one thing you must know and never forget. Google thinks the Earth is round, so that will cause distances of cities, especially at long distances, to be wrong. Google also uses the Mercator map, one of the most blatantly inaccurate maps ever drawn. Greenland on that map appears 13 times larger than its square mileage. The equator has moved downwards, and the northern hemisphere is drawn almost twice as large as its actual size. Countries that are anywhere from 10 to 50% of the size of other countries are drawn much larger. The excuse given was, it's hard to turn a ball into a flat map. But that doesn't explain why the northern hemisphere was so exaggerated, nor does it explain why Mercator chose to shrink some countries while he greatly exaggerated the size of his European employers. At a very minimum, the map is racialist. There is other map options too. Google could be using the Peters projection, which is far more accurate because at least Peters tried to draw the countries more true to their size. Why in 2016 does Google still use this ridiculous map? So is there a map that accurately shows the size of countries? Of course there is. This map is called the azimuth equidistant map. This map projects the countries on a circle, each one being the correct distance in relation to the center point, the North Pole. The Egyptians used this map for stellar maps. It matched the stars. They will try and tell you that the southern hemisphere is exaggerated, but is this true? No. If you look at the size of Africa and South America, they seem to be almost precisely drawn the same size as their square footage. Also, if it is inaccurate, then why do many modern star chart planispheres use the polar azimuthal equidistant projection? In the case of radio, this projection allows for directional antenna aiming, especially in the case of HF communications. So the answer here is, it is used because it is the most accurate map we have. This is why it is the UN flag logo, and this is why flat earthers use it. Round earthers will argue that Australia is not in the right position, but it is. This is why you can calculate sunsets 10,000 kilometers away from Australia, and this is why the sun almost never appears south of Australia, and why the azimuthal equidistant map works for all telecommunications and projections. Another point here is you get 24-hour sunlight near the North Pole during the Arctic summer, but you never get this in the South Pole. You can prove this on SunCalc, which will never show the sun to be south of the tips of South America and Australia. Also, there is one piece of footage that was claimed to be of an Antarctic summer, but that was debunked as fake. As for flights in the southern hemisphere, such as Qantas, Chile to Sydney, you can see a video of that flight, and the video shows it traveling over ice. It also shows the passenger speaking in Spanish, very frustrated that the GPS disappeared and stopped moving in the Pacific Ocean. Well, the GPS probably disappeared because they didn't want to show them where they were actually going. If you head west on a globe straight from Chile to Sydney, you would never detour south. So the only way you would see ice is if you traveled over the North Pole or nearby it, which is exactly what they did. There is almost no direct flights in the southern hemisphere. The ones that claim it are constantly delayed, or you have to phone in where they end up giving you a different flight with a stop, or they're extremely expensive and the sites usually list clearly incorrect flight times and hours and other confusing data on the sites. The reality is that there's almost no direct flights, and the ones that do exist could probably fly a little bit faster without the passengers knowing. There's already many videos on this subject. All flights mapped on the azimuthal equidistant map are almost always straight lines, because why would the pilot waste gas? On a round-Earth Mercator map, impossible nonsensical detours are made. Okay, so when we have our distance, we can then find the height of the sun. So far, a few assumptions have been made. First, that the distance we have is 100% accurate, and second, that the elevation angle given by SunCalc matches the actual elevation angle at the day and time you are trying to measure it for both cities. The first city must be 90 degrees below, and the second city must be the exact distance, and you need to know its elevation angle. For now, let's just use SunCalc's numbers so you can see how it's done. After all, this is only to show you how to triangulate. We now have all the variables required to calculate height. We then go to a 90-degree triangle calculator. We enter the distance to the city below the sun, and we enter the angle of elevation, also called the altitude, and voila! We get the height of our sun. Now, this same method was used by the infamous Eratosthenes thousands of years ago using stick and shadow. By the way, isn't it ironic that round-earth believers will mock flat earthers saying we believe in old theories, yet they constantly use a guy who's been dead for 2,000 years as their go-to argument for sun angles? Even when, for those 2,000 years, the leading theory was flat Earth? Round Earth was only popular in European-ruled countries, and even then it was unproven and constantly debated. Only when there was the advent of radio and television, and then NASA went to the moon, did the world change its mind. Anyways, Eratosthenes used a stick and shadow method for measuring the height of the sun. However, he was unable to determine the height, so he assumed we were on a curve. You see, if the Earth is curved, you only need to know the angle of elevation, and not the sun's distance. Very convenient. We don't have to care anymore. You see, in a curved model, the sun can be anywhere along the same tangent as long as the diameter of the sun matches our perspective, because in this model the sun's not moving relative to the Earth. Even though they say it zips along the universe at a zillion miles per hour, however, the problem it avoids solving, it creates hundreds more. For example, if you try to calculate the sun's distance using known cities with the assumption of a curve, you get some pretty ridiculous results ranging from 1 million to 100 million miles. Sometimes the stick will be pointing away from the sun and you won't be able to calculate it properly. Imagine trying to shoot a pole ball into a hole that's 100 million miles away. Could you do it? You can see how many times the sun's estimated distance has changed for the round Earth model over the years, with margins of error of 100-fold. This obviously is not the scientific method. You have literally zero margin of error, and it absolutely does not match what we measure with stick and shadow when we are strictly trying to know the sun's height. So why would people who believe in a round Earth force flat earthers to follow strict measurements that they themselves don't follow? How can a citizen determine the sun's distance on a round Earth? They can't. Only space agencies claim to do this, and here's why. You see, calculations of the sun distance have been made by looking at the alleged parallax of Venus over the sun. They don't share the intimate details of this test, and I doubt it could produce the same results twice. This number cannot be calculated without assuming the distance, trajectory, and speed of Venus, assumption built on top of another assumption. They say they determine Venus's distance by transferring radar signals to other planets, something based falsely on the speed of light, which we will discuss later. And of course, results that can only be confirmed or denied by government space agencies. Because, you know, you and I aren't going to be able to fly to Venus anytime soon. The flat Earth model does not believe that planets are terra firma. They are just lights, which makes sense because they appear to emit light. The flat Earth doesn't make many assumptions. Instead, they constantly research and they perform scientific experiments that anyone can perform. Although in this video, we have speculated on different theories for the moon and chemical makeup of the atmosphere. However, this is done to hopefully inspire more research into the subject. The stars and heavens remain mysterious until we know otherwise. This follows the scientific method. Until the problem is solved, we remain agnostic. However, there is a lot of videos on the subject of CGI and how preposterous NASA's images of the planets are. It's like they don't even try. Okay, so the results of my experiment were as follows. As you can see, the sun appears lower the further away it is from the center point. Why is that? Because they're assuming a curve, so that would cause the predicted elevation angle to not have our distance in a straight line, causing a steeper angle up until sunset. Using SunCalc, the closer you are to the sun, the higher the result. Keep this in mind because the higher the sun, the higher the elevation angle needs to be when the sun sets 10,000 kilometers away. This means the more air that it needs to block the sun, or the lower it must appear due to converging lines of perspective and, of course, refraction. Also, I've noticed that a lot of people do the stick and shadow experiment in relatively nearby cities, and I've noticed that there isn't really that many stick and shadow experiments done near sunset. Anyways, we are not going to use SunCalc. We are going to use real measurements from real people. And guess what? It's extremely hard to find anyone on YouTube who filmed themselves using the stick and shadow method and gave their time and GPS location. But I did find one video from Poland made in 2013. Let's take a look at their results. Here is the link of SunCalc for you to calculate the angles from the results of the Poland experiment. Now at this location, SunCalc says the elevation angle is 45.73 degrees. SunCalc is usually set for a universal time, and they might subtract or add hours depending on your IP address. In our case it was UTC minus 7, which is 3 a.m. UTC, which is 10 minus 7, which is exactly 12 p.m. in the time they listed in the video. The Polish kids measured 43 degrees. That's off by almost 3 degrees. But of course, these angles will never be accurate because of refraction. So if the Earth is round, then why do the results of these kids not match SunCalc's predictions? If we were to triangulate that shadow to calculate the sun based on a curve, we would never make it to our 93 million mile sun. But in a flat Earth, it's okay because the sun's close and we care about knowing its nature and distance. So now I'm going to choose a city on the equator. I chose this location. Okay, so that's apparently 4,880 kilometers away from our Polish kids. This makes the sun roughly 2,830 miles high. Great. So now we know why flat earthers thought the sun was anywhere from 1 to 4,000 miles high. So let's now find out the angle at which the sun should set. Remember, 4,880 kilometers is extremely far. That affects our results too. So let's go back to our triangle calculator and plug in these numbers. We assume the sun will set at about 6,200 miles away, or 10,000 kilometers. Now we get 24.5 degrees for the sunset. For the time being, let's ignore refraction, because now I want to talk a little bit more about air density. If we use our triangle calculator, we can start to find out how far and high our wall of air needs to be to block the sun at this extremely inaccurate angle. This is being done just to prove a point. At 50 miles away, with 20 miles of atmosphere, there is 54 miles on the hypotenuse of lower atmosphere blocking the sun. That's 54 miles of dense atmosphere, clouds, water, and other things constantly refracting the light. That's at an elevation of 21.8 degrees. However, it's below our target, so why stop there? The atmosphere extends 300 miles upwards at least, according to the internet. First, let's show some other possibilities. If we assume that after 80 miles away and 50 miles high of atmosphere, we get 32 degrees, which is far beyond our target. We can obviously play with these numbers to look at different angles and distances. We can even calculate a 24.5 degree angle to 6,200 miles and determine how much air is included on the hypotenuse with each mile of elevation. Now, why was a 50-mile high wall given as an example? Well, because the atmosphere doesn't stop at 20 miles, that's why. And beyond 50 miles is the thermosphere, and they consider that outer space. In fact, even at 50 miles, you can still have clouds called noctilucent clouds. If you check online, you can even see different air density estimates for different elevations. But who actually goes higher than 20 miles to measure those numbers anyway? Oh yeah, that's right, government space agencies. So we're back to trusting them again. But wait, if air pressure is so low, then how the hell do we get clouds above 50 miles? Well, they say those are rare. But here's the thing, those clouds can't form without some sort of density in molecules in order to form them. So just because there isn't clouds doesn't mean there isn't molecules. That's why the sky lights up so bright for the sun and changes colors when the Earth's magnetic field causes the aurora and ionizes different chemicals in the air, which causes all kinds of beautiful colors. And even where it appears dark, there is still very much something there. The two most buoyant chemicals on the periodic table also happen to be ordered first, our old friends, helium and hydrogen. The world record for altitude in a balloon was 32 miles. That should tell you something, that the air in the balloon was not enough to blow up the container. Then it popped, of course. So, okay, apparently there is enough hydrogen up there to form clouds. Remember, things that are less buoyant are not necessarily less refractive. Everything depends on the element. Considering that, on a clear day we can see 50 miles ahead, but then we can't see through the clouds right above us. That means that the high-altitude air can also be effective in blocking the sun. It depends entirely on the elements there, such as the makeup of a cloud. Considering they say the atmosphere stretches 300 miles up, and at only 30 degrees, you have to cross 600 miles of molecules on the hypotenuse. Look at this company, Air Swimmers, for example. They make these balloons that look like flying fish, and they just hover in the sky. How do they do it? Well, you find the perfect buoyant balance to the fish by adding and removing putty, and then you can get it to suspend in midair like a cloud, and then you propel it with its fin. Any balloon can be made to hover mid-air if the correct balance is found. This is most likely one method on how airships can find balance. For example, if you had an air intake, you could probably find the perfect balance to keep the balloon stable in the sky. I should also mention that heat also plays a role and causes air to expand, changing the volume. And thus heat is another method to increase elevation. It may also explain why parts of the thermosphere is less dense to begin with, because it's hot near the sun, and when things cool, they contract, so consider all of this. There are even more elements at play when we are seeing the sun set. First, there is perspective. Can we see the sun? And second, there is whether or not the light is lighting us. The two are not related. For example, even when the sun is blocked by the clouds, it still lights us. The reverse is also possible, and I will give you an example. Let's take the example of the moon. The light is extremely powerful, but it doesn't light up the whole atmosphere. The moon's light doesn't appear to have the same qualities that the sun's does. However, it's still visible. Another example, a small light in your house only illuminates locally in a corner, but it won't light the whole room. In fact, the rest of the room might appear dark. Lastly, if we go into the depths of the ocean, the light is always blocked by something. It never travels far. At the ocean depths, light won't even go more than a few feet. This is important because flat earthers have said diverging perspective lines can cause the sun not to be seen. However, they probably didn't consider that the light could illuminate things near you. However, when you add refraction, then the light might not reach you. This is why air density is important. Okay, but let's not rely on converging lines. Let's try to explain perspective with converging lines. Now, if the sun is at a higher angle, why would it appear on the horizon? Well, first of all, the horizon we see is not the true horizon. It must be a little higher, as proved in the air density video. Second, as things move to the horizon, they appear lower, and the altitude of things make them appear angled. This is why it's so extremely hard to determine how far stars are. To us, they are lights in the sky with no apparent parallax. Without parallax, the only way to know a star's position is triangulation, but for that, we need to know the angles to the stars. But you can't know the angle of something based on its visual appearance alone. You can see where it starts getting difficult. Our eyes triangulate things, but the further something is, the harder it is to determine its distance because of perspective. This is also true for multiple cameras and 3D triangulation of points. It's a common problem in computer science. That's why 3D reconstruction is so much easier with parallax and distortion of known patterns, like in the infrared projector on a Kinect camera, or by using multiple photos. If you enjoy the subject of perspective and higher level math, then I'm going to recommend you watch videos about projective geometry by Norman Wildberger, who gives amazing PhD level lectures on the subject. This subject used to be taught in all schools before the 20th century, but they stopped teaching it for some reason, something that Norman laments. He seems to think our math has actually gotten less rigorous. Perhaps that's why there was so many good artists in the Renaissance period. So let's take a look at this video by Fouquet World. The video is actually pretty brilliant. He shows not only the size of things getting smaller as they approach the horizon, but how they also seem to be affected by the angle of approach. In this example, the vehicles converge to the center point of his measurement. Despite going straight, they all seem to converge to the center at 23.5 degrees. This is a funny coincidence that his observation matched the round Earth proposed axial tilt. What he also shows is that over and over again things dip below the camera's perspective despite being on a flat road, mostly because perspective and extremely small bumps in the road. Also, our eye's lens is curved, and so is the lens of a camera, and this is something that I don't really see discussed often. Now, we already know that wide-angle lenses causes things that are far away to curve. This is why fisheye lenses are totally ridiculous choices for filming the horizon. But at what point does the lens in our eye affect the angle of elevation, and at what point does it cause things on the horizon to converge? After all, the further away something is, the more likely it is to be affected by the curvature of our lens. You can try a pinhole camera, but the pinhole camera model does not include, for example, geometric distortions or blurring of unfocused objects caused by finite-sized apertures. It also does not take into account that most practical cameras have only discrete image coordinates. Its validity depends on the quality of the camera, and in general decreases from the center of the image to the edge of the lens, and distortion will increase. So how can we know with 100% certainty that our visual angle to the sun is not affected by any of these things? And can we know that light from the sun can reach beyond 6,000 miles away? Especially when light doesn't travel more than a few feet in the depths of the oceans. After all, when an eclipse happens, it gets dark, but we can still see the sun. So what gets illuminated and what can be seen are separate issues completely. If the vanishing point is slightly angled and the objects that approach the horizon appear lower, it's also unclear that you would be able to visually prove that the sun cannot be flush with the horizon or diverge below it due to optics. It's fair to say it never sets at 0 degrees anyway. So what does this mean? Well, if the sun turns out to be 1,000 miles high or less, then we only need to account for a 9 degree or less elevation angle at sunset. This is pretty ideal. The sun may even be less than 500 miles high. When you start to seriously study chemistry, our atmosphere, electromagnetism, refraction, and optics, an unlimited amount of doors will open for you. So the different ideas work together perfectly, and you can see how important it will be for people to continue research. And then they start to say things about the thermosphere like that it reaches 2,700 degrees, but then they make excuses as to why that won't melt the ISS. Brian Mullen had a very good video on the subject. If they claim to not be melted at that height, then how did they measure the temperature to begin with? And whatever is making the particles hotter, shouldn't that also be heating the ship? One possible explanation for the temperature increase in space is simple. They're close to the sun. We might see it go from extreme heat to extreme cold. All kinds of elements could be generated up there, maybe highly refractive elements, further layering our atmosphere. After all, if the Earth is flat, why should we assume the sun and moon are flying through a vacuum? Especially if we know that NASA is feeding everyone false information. It's much more believable that the sun and moon are something so unbelievably awesome that it would humble and amaze all of us. Also, light changes speed in water and gas. This is very important, and when you realize this, you will be amazed at how much modern religious scientism falls apart. Light can slow down anywhere from 3/4 to 1/3 of its speed through water and glass. And using a crystal, you can even trap light. By use of a Bose-Einstein condensate, Danish physicist Lene Vestergaard Hau at Harvard University succeeded in slowing a beam of light to about 17 meters per second. Okay, so why does this matter? Well, there are many things you can do with light. You can refract it, changing its direction, you can diffract it, you can separate the waves, and sometimes isolate color frequencies, like Royal Raymond Rife did to analyze bacteria without harming it with the world's most powerful cellular microscope that he made. Or you can reflect it. So this can be an important problem because modern scientists base all of their measurements on c, the speed of light, which they calculate in air. But remember, air is filled with at least 30% humidity and tons of other chemicals that refract light. It's not even close to being transparent. There is so much air pressure that it can cause planes to rip apart if they fly too fast at low altitude. They never measure this speed on Earth in a vacuum chamber. Their official number for C is based on experiments done in lower atmosphere, which we can prove because people actually measure this and post those videos to YouTube. They might use an oscilloscope and a mirror, for example. Let's also consider the margin of error in their measurements and in their equipment. Now, if you are not measuring C in a vacuum, then how can you know its true speed? It clearly moves slower in air, so the speed of light must be wrong, but how much is debatable. However, if you suck the air out of a train, it will crush like a tin can. Sending lasers from Earth to be refracted back won't work either, because it still needs to travel through the atmosphere. So who can measure light in a vacuum? It's possible that it's almost infinitely faster. So why does this matter? Because it debunks the speed of light and brings relativity into serious question. But don't take my word for it. Let's look at this video by Norman Wildberger again. He does an absolutely brilliant job showing you mathematically why GPS would not possibly work without relativity. The math is absolutely beautiful. He brings up the Michelson-Morley experiment, which proves the Earth wasn't spinning, because no matter what direction you measure light, the result is the same, even in the direction of the alleged spin. The globe Earth was basically screwed by the experiment. Norman starts talking about relativity in GPS at around 20 minutes. So the problem with satellites is they have to use atomic clocks and measure time extremely accurately. They say many satellites are 23,000 miles away, for example, or even more in some cases. So right off the bat, you know that anybody who thinks they have seen one has obviously had it confused with a weather balloon or something else. Nobody is going to be seeing anything 23,000 miles away. Second, the satellite somehow had to get past the blazing hot thermosphere, and third, why the hell would anyone send satellites 23,000 miles away when they can just use weather balloons or skywave or fiber optic cables or ground-based towers, which is exactly what they do. And of course we have no videos of the Earth spinning and no photos that aren't CGI composites. If those satellites were real, there would be thousands of videos of the Earth spinning and thousands of photos. Well, one thing that is certain is light can move longer distances vertically because there are less obstructions and it's moving through a less dense medium. Technology such as skywave, for example, has been around for a very long time, and it functions by reflecting waves off of the ionosphere. A similar effect can be achieved with balloons, sending signals from one to another. Now, Norman is a genius mathematician, and he explains that the results of GPS and its ability to triangulate would be off by milliseconds. Then he uses relativity in his math to fix the problem. So he's forced to use relativity here. Relativity says that time slows down the faster you approach the speed of light, but only for you, the time traveler. So because the Michelson-Morley experiment didn't fit the globe model, and because their fake satellites would have latency, they decided that everything travels through time. First of all, Norman makes some assumptions. First, he assumes that the speed of light is correct. But we already know that light was measured in the atmosphere and not a vacuum, so it can't be perfectly accurate. So his first assumption is based on an incorrect number. Next, he assumes the government is telling the truth and that there are satellites 23,000 miles away. Now you tell me, what is more logical? Is it more logical that light travels through time, or that the speed of light was wrong? Is it more logical that light travels through time, or the government lied about satellites? Does light travel through time, or does the Earth simply not spin? Does light travel through time, or are satellites actually just balloons and skywave and ground-based technology? Tesla was one of the greatest minds in history. He discovered alternating current. It says he discovered the radio before Marconi. He invented more things than almost anybody of his time. He was literally the father of all of our modern technology. And he didn't believe in relativity. He also did not believe in the atom molecule, and he believed that electrons were physically impossible. Look at some of these quotes by Tesla. He was obviously a huge fan of the geocentric model. Tesla believed in the scientific method. He did not agree with the idea that you make up a theory to explain a phenomenon. That is the reverse of the scientific method. It borders on religious dogma. Tesla would lament that science moved away from experimentation and into math and conjecture. But Einstein didn't care. He's famous for saying, if the theory does not fit the facts, change the facts. In other words, what he's basically saying is, I'm right, and if you don't agree, I change the laws of your reality.
We are men of action. Lies do not become us.
Well spoken, sir.
Relativity is just as nonsensical as his idea of gravity bending space. They always show you space bending on one plane, but if gravity bent space, it'd have to bend it in all three dimensions on all planes simultaneously, which is basically the same as saying nothing. And they made Einstein the man of the century instead of Nikola Tesla or Mahatma Gandhi or somebody else. Where Tesla gave us the modern world, Einstein gave us mathematical excuses. Also, if the speed of light is wrong, then light years are wrong, and so is every calculation that space agencies do. Stellar parallax was in constant dispute in the early 1900s. If you can't accurately determine the exact angle of refracted light, then why on earth would you think you can determine the parallax of a star? Well, there is no stellar parallax, and it is much more logical to assume the stars go around us. Otherwise, the stars would move in synchronicity and force scientists to assume the galaxy is flat. Scientists also assume that the solar system is flat. But how can the solar system or galaxy be flat? That is a statistical impossibility with no regard for 3 dimensions. Believing this is almost a religious belief. Why do people agree with this? So who's the bigger flat earther, us or them? I have an idea. Don't assume the galaxy with its alleged zillions of stars is on a flat plane, and instead simply assume the Earth is flat, exactly as it appears. They never even give a satisfactory reason as to how they think the solar system became flat in 3 dimensions. I doubt you will even find a working computer model for that theory, although I'm sure somebody somewhere has made us a pretty animation. Most modern theories are hardly ever questioned. If the subject of stars interests you, I highly recommend you investigate this further. So what about a theodolite for measuring angles? Well, surveyors use them all the time. They are, however, not very useful for extremely long distances. Not to mention, as distances increase, so does your margin of error. So another question about the sun is, if you use a solar filter, then the sun will not shrink in diameter. Well, first of all, there is very little footage, if any, of the sun for 24 hours through a solar filter sunrise to sunset. Also, most of the footage zooms in on the sun. This makes a continuous shot a lot harder. However, thanks again to Phuket World, who shot the sun through a solar filter, and he posted his results, and we do see a diameter change. However, round Earth believers give us their videos showing the size not changing. However, most of these videos are very short and thus inconclusive. So which one is it? I would like to see the Flat Earth researchers perform a 24-hour time-lapse with a solar filter and no zooming so the shot is continuous. Also, the atmosphere refracts the sun and it increases the diameter of it as it passes through air. The further the sun, the more air it'll pass through, and the more it won't shrink as much as we expect it to. This was explained in my first video. Also, it depends completely on the light source and the lens of the light source. For example, when you use a projector, the image actually gets bigger as you get further away from the projection. By the way, in my first video, a few people wanted to know how I can prove that we were walking backwards. Well, you see the diameter of the light shrink, and in one shot you can see the light overhead. The reason it descends so fast is because we sped up the footage 300%. In fact, you can tell a lot of the clips that we used were sped up to fit the video within the audio and get it within 10 minutes. We walk backwards from the table in the room to the end, which is about 15 feet away. Plus, you can do it yourself. Do it with 2 cameras if you like. Do it with the lights on even. The results will be the same. In order to set it up, just use transparent sheets, cut them into different heights, and stack them on top of each other. The more sheets for each layer of atmosphere, the denser that layer of air. You can also experiment with different gels and simulate different elements. Some people ask, why does the sun approach left to right or right to left in different hemispheres? Well, obviously that depends entirely on which way you are facing and if you are north or south of the sun. I've noticed that people use these videos where they show a stick and shadow going around a little piece of paper with north marked on it. But this is clearly wrong, because if you are south of the equator, the sun will be approaching from the east, which will be on your right-hand side if you're facing north, and it will cast a southerly shadow on the stick. As it moves from right to left, the shadow will appear to move counterclockwise. If you perform the same stick and shadow experiment north of the sun, the shadow will move in the other direction. Of course, the sun can't change from clockwise to counterclockwise. The sun's path at the equator is never straight up and down. On a flat Earth at 90 degrees under the sun should always swing in slightly northernly. Also, the equator is not possible in a round Earth model. The equator's position in both models depends entirely on the season. In a flat Earth, the sun traces different circles spiraling outwards for the seasons. And around Earth, you can't have an equator because of axial tilt. This causes the Earth to be on one side of the sun 6 months later. The side of the Earth that was tilted towards is now tilted a ways. That's their explanation for seasons. But it doesn't actually make any sense. Look what would happen to the South Pole. If the South Pole was ever exposed to the sun like that, the temperature would rise dramatically. But if you compare North and South Pole temperatures, the South Pole is always a lot colder. So which model better explains seasons? Easy, the flat Earth model. The flat Earth model has the South Pole along a much larger line and further from the Sun. Also, equatorial countries keep a very consistent temperature year-round, and northern cities get unbelievably hot, like Vegas and Mexicali, despite being slightly above the equator. This is because, in the flat Earth model, the Sun spirals inwards and outwards depending on the season. In the flat Earth model, the Sun spirals would average in the center of the equatorial line, giving a pretty consistent temperature, but it would move slightly above and below it to account for seasons and would still be distant enough to set from everything. We can also measure 10,000 kilometers from every single point from where it sets. Both models explain varying daylight time, but the round Earth suffers from the fact that the Earth is on the other side 6 months later, forcing them to prove the impossible. Why isn't day and night not flipped 6 months later? So the flat Earth is a lot more modest in daylight times. If the Sun is further south, it circuits near the southern hemisphere countries for much longer. Also, the Sun's speed in the flat Earth increases during that time. Then it spirals inwards into a smaller circle. Some people have theorized about a dome, and although that's a very interesting idea, it's a little bit beyond the scope of this video. There are many theories out there. Some think there is more land, some think there is a dome. What is absolutely certain is we are not on a spinning ball. Also, crepuscular rays is strong evidence that the Sun is a lot closer. A great video by P-Brain was done on the subject, where he shows how the light angles would come in. Now, you might say that this is due to perspective, but the problem is crepuscular rays are pretty localized. There are also hotspots from the Sun, and the angles of crepuscular rays are extremely sharp. The Sun appears closer because it is. Finally, we come to one of my favorite subjects, and that is the subject of Fata Morgana. Fata Morgana is a complex form of superior mirage that is seen in the narrow band right above the horizon. This optical phenomenon actually dramatically favors the flat Earth. In my previous video, I explained how the waterline can appear slightly higher due to the tremendous amount of water particles near the water's surface, which can form an inferior and superior mirage. Fata Morgana is usually layered and usually inverted, or both inverted and straight. Well, when you zoom in on the horizon, you are only looking at this extremely thin line of the horizon. It becomes pretty self-evident that after 40 miles, strange things can start to happen with compounded air. What do you notice about every mirage that you see? Well, first of all, they're completely awesome. They're also pretty common over water and over the hot desert or in extremely cold climates. This mirage here is awesome. Look at how it looks like a flying ice wall. One thing that most mirages have in common is they are wavy, with fractals, and sometimes they look ghostly looking. Compared to the time-lapse of the Chicago skyline, there is absolutely no way this is a mirage. It looks nothing like the images you just saw. The entire city is intact, and there's no wavy lines or inversion layers. Also, things that you can see within 10 miles away at sea level, like boats, islands, and other shorelines and so forth, should be more than 6 stories below your line of sight. These are daily occurrences. Go to the beach and prove it to yourself. And remember, it squares with each mile on a curve, so each mile becomes more and more impossible to explain on a ball and easier to explain on a flat plane. We can even see some things up to 100 miles away on a day with good clarity. So we can obviously tell the difference between what is and what is not a mirage. Look at this crazy mirage over the desert road. It looks like the road is a pool of water and the car drives into it and almost gets devoured by the light. Now, an inferior mirage usually causes the illusion to appear below, and a superior mirage usually causes the illusion to appear above. The superior mirage is usually considered a little more stable because cold air stays below on the horizon line. However, any air current or heat on the water from the sun will cause the heat to mix with it, and that's why they're extremely rare. Flat earthers avoid the subjects of mirage and refraction, but this should be their favorite subject. It usually works in their favor. Superior mirages are more common in northern climates over ice because there the air is cold enough to make the effect more probable. If inferior mirages and Fata Morgana are more common, then we can prove that the majority of mirages are actually unstable. This type of mirage is commonplace in the desert and over lakes. Inferior mirages are not stable. They will constantly shift and change forms. We have been told that mirages are more common near the horizon line. So if people are saying that the Chicago skyline is a mirage, then they must give examples of inverted cities and prove that this is a common and everyday occurrence. Also, because air density forms a gradient, it's unclear that a superior mirage would be able to happen to an entire city over a lake. And also, you can see the Chicago skyline any day you desire. The visibility in the time-lapse of the skyline is obviously due to clarity. When the clouds clear, it's visible. Also, this is just one of tens of thousands of examples. Any day you can visit the Bolivian salt flats or see mountain ranges or cities for miles. You can see other islands and boats on a daily basis. So if inferior mirages are more common, would it not be more reasonable to assume that it has an effect on the waterline, normally causing the waterline to appear slightly higher? And also consider the effect that our atmosphere has on light. When you study it, you will be amazed and your eyes will open and you will know the truth. So hopefully this video has been helpful. I'm going to attach a frequently asked questions to this, so researchers can make their own videos based on what they have learned here. This video is meant to be a very high-level analysis of the sun, angles, refractions, optics, and other things that have not been covered enough in the Flat Earth movement. It's an extremely advanced course in optics and light. We have tried our best to avoid speculation and to explain light in as great a depth as possible. If there was any errors or omissions in this video, please consider the amount of content we've covered, the amount of time it takes to make a video like this, and please be kind in the comments. We realize there will be a lot of discussion on this video and the subjects that it covers, so try to make logical and scientific arguments that can be reproduced at home and avoid breaking any of the following logical fallacies. You can pause here if you need time to read them. Also, you have permission to mirror this video. You can use it to make smaller videos, or you can borrow ideas and content from it. In fact, anybody that wants to make my FAQ into a video or a documentary, they are certainly welcome to. All I ask is that you choose really good videos and visuals and links to illustrate the points. And remember to stay positive, don't worry, and be happy. Thanks, and have a wonderful day.
There goes the moon. Now, somebody explain to me what is going on.
Inconceivable!
How is the moon moving across the screen? I'm not doing anything. The button's on play. You can see the time in the lower left. Oh, little left-hand turn. And they're off. Oh, it stopped. So maybe it's going to hang out there for a little bit. Because we all know the moon moves so slowly around the Earth. It takes 20... Oh, wait a second. The moon's moving. Holy smokes. Watch out. It's going to hit us. Yeah, that's real. So honestly, I need one of you NASA groupies to tell me what is going on here. Please explain it to me. My imbecilic mind is not capable of scientific thought, I guess. So you'll need to come in and tell me what's going on, because that makes no sense.